There we go.
When the smoke clears, you and I against the world, that's what you told me.
Seeing cars, people, roads, and the world around me. Constantly aware of my surroundings in the dark, the rain, and the snow. I am a learner, giving robots the skills to perform human tasks and mastering the art of driving by watching others. I am a protector, watching out for your safety.
Caution, just a moment. All clear.
Even when others are not.
Cross-traffic danger.
That was ILA.
All clear.
I'm a helper, giving you a hand when yours are full.
Hello.
And assisting the disabled in their homes. I am a navigator, planning a safer path and showing you the road I'm taking. Powering robots that make the things we need. And those that create original works of art in the style of the masters. I am even the composer of the music you're hearing. AI, brought to life by Nvidia, deep learning, and brilliant minds everywhere.
Ladies and gentlemen, please welcome Nvidia founder and CEO, Jensen Huang.
CES. It is always exciting to kick off the new year, just wondering what we're going to see at CES. And this year, just like always, we're going to see some amazing things. Everybody's talking about what they're going to see at CES, and this was just in the news. 5 big things to watch for at CES 2018. It's the year's biggest tech trade show, and this should be jam-packed with announcements related to self-driving cars, gaming PCs, VR headsets, and much more. Well, let's get started because we're going to talk about all of that and much more at our keynote tonight. So welcome. NVIDIA has dedicated ourselves to a form of computing called GPU computing. 25 years in the making, we have dedicated our entire company in developing one of the most complex and most powerful forms of computing. Because of GPU computing, we're able to synthesize virtual reality and virtual worlds. And with recent breakthroughs in artificial intelligence, we're able to understand these physical worlds, our physical worlds. We have 3 primary business drivers. The first is gaming. $100 billion industry. It is larger than ever. More and more gamers coming in. The types of game you're able to play, more and more genres, and people are gaming in more ways. This is a really exciting and a vibrant industry. I just realized I jogged up literally 5 steps, and I'm breathless. Water, please. Who put keynotes at 8 o'clock at night? It's like 2 hours past cocktail time. Welcome to CES, Nvidia's keynote. The second growth driver for us is artificial intelligence. Recent breakthroughs in deep learning has made it possible for the very first time for software to write software. And this software, using deep learning technology, is able to write software that no human is able to develop. And as a result, we're able to now solve what was previously unsolvable problems. This is one of the most exciting developments in technology. It's going to influence every single industry that we know, and it is also one of our fastest growth drivers. By applying the technology, and with recent breakthroughs in deep learning and developments in algorithm, we're finally able to apply deep learning and AI to one of the most difficult challenges of all, self-driving cars. For a car to be able to navigate through a really super complicated world and do it very safely is just an incredible and a daunting challenge. As we will see today, we're making enormous progress. This is one of the largest industries in the world. The moving of people, the moving of goods, including cars, taxis, mobility as a service, and trucking, it represents $10 trillion, the single largest and most impactful, important industry on the planet. We now have an opportunity to revolutionize it. 3 fantastic opportunities for us to apply our work to revolutionize the industry, and 3 incredibly large and growing opportunities. I wasn't kidding, 5 steps. Next time, could you guys just put it lower? It's usually 3 steps.
Give him an elevator.
What's that?
Oh, no.
It's just that I practiced doing that twice already today. And so, every year that clicks by, for many in the audience, first of all, it's great to see so many friends in the audience. So. To see all of you come year in and year out. I've been doing this for 25 years. And so even though my shoes look young,
let's see if your brother
the
knows
body is not. Incredible times. GeForce is the world's largest gaming platform. 200 million gamers in every country in the world. It is the largest gaming platform in the world. It is also the most vibrant and active gaming platform in the world. Because it's a PC, because it's an open system, it has the ability to continue to be vibrant and evolve and adopt new technologies. We believe in a couple more years, the experience of VR is going to get even better, thinner, smaller, more elegant head-mount displays, wireless, inside-out tracking. All of those technologies are going to make VR even more exciting. Gaming is no longer just about gaming, it's a sport. In fact, it is now the largest sport in the world. It's kind of amazing, but yet it's perfectly obvious. Virtual reality should be the largest sport because virtual reality can be any sport. It could be a racing game, it could be a basketball game, it could be a football game. Any game you could imagine, virtual reality can make it happen. 600 million people, more people than watch NFL football, now enjoy esports. It is the single largest sport in the world. It is also the single largest social platform in the world. More people share their experiences on YouTube, on Twitch, by playing video games than any other form. In just the time that we've made possible GeForce Experience, for you to be able to capture and share your winning moments, 1 billion people have shared it on YouTube. 1 billion people. Unbelievable. And then, of course, video games is not just on your PC in front of your television. Video game is now also mobile. The fastest growing game console in the US, the fastest growing game console in the US, after 30 years of making game consoles, the Nintendo Switch was the fastest growing. And the reason for that, by working so closely together, we were able to take advantage of our incredible technology to make it possible for them to create a game console that is amazing and mobile at the same time. The Nvidia gaming platform. Well, at this show, we're going to announce 10 new desktop gaming platforms, 3 new laptops, and 3 amazing displays. We call it the big format gaming display, the BFGD, big format gaming display. Be sure to go look
BFD.
for it today. BFGD.
BFGD.
Short pause, BFGD.
BFG.
BFGD, big format gaming display. Making it possible for you to now enjoy PC gaming in enormous displays that are incredibly fluid, HDR, G-Sync, silky smooth, gaming experience like you've never had before. Well, one of the things that we've been doing that's really fantastically successful is called Max-Q. We applied all of our know-how and all of our expertise to take this incredibly powerful processor and putting it into a super, super energy efficient form factor. And the result is called Max-Q. And it basically, we left no technology and no science out of this thing. This is how a gaming notebook, this is what a gaming notebook, hey Marshall, come on. Ladies and gentlemen, Marshall. So this is what I think I was breathless in anticipation of holding this. This is 20 pounds. This is what a high-end Nvidia gaming notebook looks like last year. Okay, so this is 60 millimeters, 10 pounds. 60 millimeters and 10 pounds. 10 pounds, at my age, it feels like 50, right? So this is 60 millimeters, 10 pounds, and this is 20 millimeters and 5 pounds. Okay, so before, after, before, after. Marshall? Oh God. You know, CEO jobs aren't supposed to be this rigorous.
Say CEO.
This is what a latest generation gaming notebook looks like. And so what do? Okay, can you guys see this?
Oh, that's dope.
This, 4 times the performance of a MacBook Pro.
4 times.
Twice the performance of the highest performance game console. No wires, guys. Look at this thing. Max-Q technology. New architecture design, process engineering, design engineering, system software, thermal management, power supply design. We tuned and tweaked and optimized every little drop of power out of this thing. As a result, inside, you have one of the most powerful GPUs in the world in this little tiny thin laptop, and you have something that is more powerful than the most powerful game console right there in your hands. Isn't that amazing? Unbelievable. So that's the Max-Q, NVIDIA Max-Q. Thank you. All right, Marsha, good job. Guys, gaming. The reason why it continues to grow is because production value continues to grow. And every time production value grows, you need more technology to be able to synthesize those virtual worlds. More gamers are coming into this marketplace. If you think about it, in the generation before me, almost very few are gamers. I was the first generation gamer on the planet. My generation started the Nintendo revolution. However, my children's children's generation, everyone will be a gamer.
And so in just 3 generations' time, no gamers to everybody will be a gamer. Someday, every human will be a gamer. This is going to continue to be a very large industry. This will continue to grow, and it'll continue to evolve, and people will enjoy it in different ways. It's now sports, it is also art. It's a way to share your passions with friends and people that you know. So Nvidia gaming, large and continuously growing market. The second growth driver for us is AI. From synthesizing virtual worlds to now the breakthrough of deep learning, able to understand our physical world, interpret and gain insight from it, and create programs automatically that allows us to take the necessary prediction or the necessary action is truly a breakthrough. We were really fortunate to have started focusing on deep learning years ago. And this last year, the progress was incredible. This last year, we announced the single most complex processor the world has ever made. This is called the Nvidia Tesla V100 Volta. 21 billion transistors. It's the largest chip the world has ever made. 12 nanometer FinFET, 3D stacked memory, using HBM2, the fastest memories in the world. In this incredible module, it runs at a voltage of less than 1 volt, and right here, 250 amps flow through its connectors. These 2 connectors in the back, called NVLink, connects it to the other 8 processors, and together it makes the most compact supercomputer the world's ever known, the Nvidia Volta. It also includes a brand new type of deep learning instruction set called Tensor Core, 120 teraflops of performance, 125 teraflops. What that basically says is that one single box with 8 processors delivers for the very first time 1 petaflops of performance. Now, 1 petaflops of performance basically puts you way up there on the world's top 500 supercomputers. It would take racks and racks of supercomputers to be able to deliver this level of performance using traditional CPUs. It's one of the reasons why we've been so successful with our GPUs in deep learning. The second contribution this year is called Nvidia GPU Cloud. The software stack of deep learning is incredibly complicated. It is basically a supercomputing software stack. You have to use the software framework to learn from data, terabytes and terabytes and terabytes of data, to essentially learn what is the essential and the critical insight in that data for the software to write software by itself. They call them frameworks. There's a whole bunch of different types of frameworks. TensorFlow and Theano and PyTorch and Paddle, MXNet. There's a whole bunch of different types of frameworks in the world. And these different frameworks are developed by different people and also developed for different types of network development and for different phases of deep learning development. We've containerized all of these software, making it possible for people to just go to the cloud, download the entire stack, which has been fully optimized, fully tuned, fully tested, and just run it in the cloud. You can download it from NGC, the Nvidia GPU Cloud, and you can download it into all of the cloud service providers who have designed in the Nvidia Tesla into their cloud data center. As it turns out, every single cloud data center in the world, from Google to Amazon to Microsoft, Facebook, Baidu, Tencent, Alibaba, every single cloud service provider in the world has adopted this processor. The very first time in history, one single architecture has been adopted everywhere. It has also been adopted by every single data center server manufacturer. There's a Lenovo or IBM or Cisco or Dell or HP. Every single server maker on the planet can now make it available to you in your data center. Go to NGC, you decide which one of the frameworks you'd like to use. register for one of the cloud service providers, buy yourself a server with Nvidia's Tesla in it, you download, you click, it downloads, and off you're going, developing deep learning neural networks. Incredibly simple. Now, if you would like not to use one of the cloud service providers and would like to own your own data center, but you don't have the technical capability to do so, or don't have the time to do so, we also containerized the entire supercomputer into one server. We call it the DGX. DGX is the most complex one computer that has been built in recent history. This is the DGX supercomputer, 8 processors, 1 petaflops, connected with NVLink in a 3U server. It comes right out of the box. All of the integrated software is ready to go. You pull it out of the box, you plug it in, you have a supercomputer ready for deep learning. And if you would like one on this side, we call it DGX station with 4 GPUs. Completely liquid cooled, completely quiet. And so the processor, NGC software stack, all of the cloud service providers and all the computer makers, and the DGX station makes it possible for you to do deep learning for any cloud, in any data center, and for any type of computer. Now, once you're done with the deep learning development of the neural network, you have to optimize it for the computing runtime we call inference of your computer. Depending on whether you want to do it in the cloud, in your data center, for different types, or maybe embedded into a car, that neural network has to be optimized, and the optimizing compiler is called TensorRT. The performance improvement running the output of that code, the computational graph that comes out of the framework, into TensorRT, the optimization is incredible. Another 2, 4, 6 times of performance. And when you're done with that, if you would like to do deep learning on your own PC, we have a brand new computer, brand new processor called the Titan V, and it is the most powerful PC GPU in the world. This is the Titan V. It was available just a few weeks ago. Demand is fantastic. $3,000, the most powerful GPU for your PC ever made, and it replaces basically supercomputers, okay, the Titan V. And so, thanks, Paul. End-to-end, development of deep learning, from the processor to the software stack, cloud service providers, data centers, workstations, inference, optimizing compilers into your PC, from end to end. Every framework, anywhere in the world, everywhere in the world, cloud, data center, on-prem computers, from training to inference. That was our achievement last year. The team did an enormous amount of work. As a result, deep learning researchers all over the world can now get their hands on the supercomputer so they can accelerate their development. Well, the reason why we're growing so fast is because the value proposition is absolutely incredible. And this is, give you an example of what it takes to do something like inference. So this is 45,000 images per second. It takes 4 racks, 160 CPUs in order to do 45,000 images per second of Resonant 50. And you could do so with 160 CPUs, which consume 65,000 watts. 65,000 watts. Now, if you were to use the platform that I just described, then it looks like this. 45,000 images, 4 racks, 160 CPUs, 65,000 watts, or 45,000 images per second, 1 single node with 8 GPUs and 3,000 watts. 1/6 the cost, 1/20 the power, 4 racks reduced into 1 box. That's the reason why people are jumping on the Nvidia GPU for deep learning. Before, after.
Before, after. And so the takeaway is simple. The takeaway is simple. The more you buy, the more money you save. And so if there's one thing that you remember, if you could just... All of the technical jargon is just nonsense. You just remember, the more you buy...
What?
And just go back and tell everybody, the more you buy from Jensen, the more money you save. Incredible savings. I mean, it's just shocking, actually. It's shocking. And so that's what it looks like. But let's see what it feels like. Let's see what it feels like. And so we're going to give you a demonstration. You know, this is the amazing thing about deep learning. Deep learning, we're going to use this program that's been trained to recognize flowers. And it's been trained to recognize images. Now, I just want you to imagine this. Imagine there's a whole bunch of binary numbers that comes into your program, and your job is to figure out what kind of flower it is, And several years, I demonstrated for the very first time to a good friend of mine this deep neural network for recognizing dogs, and it didn't do a very good job. But I would like to redeem myself today by using it to recognize flowers. And the beautiful thing is that we're going to recognize flowers that you don't even recognize, so you have no clue whether I'm right or not. And so this is a demonstration of recognition where the audience has no idea whether I'm going to be right or not. But here's the amazing thing. Here's a software that has learned by itself how to recognize these amazing species of flowers from the ones and zeros that comes into this network. If you were to figure out how to write this by software with your own hands, I have no idea where to start. And so let's go ahead and, Matt, are you back there? Let's give them a demonstration. So this is what you're looking at here is called inference, to infer using this artificial intelligence network, and the name of this network is called ResNet 50, to infer what is the flower. Let's stop somewhere so that we can actually see. Can you, there you go. So that's a foxglove. That's a rose. Okay, so far so good. Sword lily. Giant arum lily. Petunia, that one's easy. Frangipanni, those words never came out of my mouth before. Pelargonia, okay, windflower. And so, sword lily. I mean, the truth is that I could have put anything up there. You guys probably wouldn't know the difference. But it's amazing. It's able to recognize with superhuman levels of capabilities all of these different types of flowers. What's happening here is that this is running on a CPU. This is the latest generation CPU, Skylake. It's been trained on a framework called TensorFlow. This is using the latest generation CNN network called ResNet 152. 152 layers of mathematics. 152 layers of mathematics. And then it infers that that is a common dandelion. And it's running at a performance of images of 5 images per second. And so basically 5 people on their cell phone could have taken a picture of the flower, sends it up into the cloud, and within 1 second's time, 1/1000, it comes back. 1 second's time. Okay, billions and billions of cycles, trillions of cycles of electronic cycles later, it comes back and it says that's a foxglove. This, obviously, if we would have shown this to you 10 years ago, or even 5 years ago, even 3 years ago, this would have been a miracle. And quite frankly, it still kind of is a miracle. But let's show you what it looks like if we were to run it on the stack that I told you about. Okay, so this is on. So what's happening here? We're taking the exact same network. We're running it on one of these. Okay, do you see that? So instead of one CPU, we're running it on one V100 Tesla voltage GPU, and it's running at 911 images per second. 911 images per second. Quite a bit faster, almost 200 times faster. Okay, so if we were now to put these 8 into one node,
Matt, could you show that to us? All right? And so 7,000 of us, we have hundreds in this room. So we invited all of our friends, and we took a picture of a flower, we sent it up to the cloud. Instantly, it would come back and tell us what that flower is. Now, the amazing thing is this. Let's do some simple math. So we now have 7,000 images per second. One node of CPUs, of servers, is 2 CPUs. So it'd be 3,000. So if I divided that by 2, so one GPU node is now 3,500 times. And if there are 40 nodes per rack, it would be close to, what is that, 20 racks. Close to 20 racks. And so what that basically says is that this thing here would take 20 racks. Okay, so a server with 40, a rack of server with 40 different servers would take 20 racks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Before I run out of breath. Okay. Right here. That entire stage would be filled with computers, and it could be replaced with this. That is the power of GPU for deep learning. So the message is very, very clear. It's abundantly clear. The more you buy, the more you save. Thank you. We accept all credit cards.
Bitcoin?
All right. The thing that's really amazing is this. Obviously, for image recognition, for speech recognition, we've now achieved the superhuman levels. Superhuman levels. Nvidia has been doing a lot of research in artificial intelligence. Our first mission is to create the enabling platforms for every developer on the planet, whether they want to do it in the cloud, in a data center, on-prem, in a workstation, or PC, to be able to advance deep learning. We think that this work is so incredibly important, and the type of problems we're going to be able to solve, the unsolvable problems, are so powerful that we have to enable everybody everywhere. Well, meanwhile, we also want to advance the research ourselves. And there's several of these are already on the web, and so you can go look them up. This is using it for ray tracing. Ray tracing here, all those black dots are where the beams of light haven't reached yet. We could actually use artificial intelligence to guess, to predict what is likely the color that it would have produced. It would have produced. And as a result, we sped up ray tracing by a factor of 10. We taught a neural network to watch how faces animate when it's talking. As a result, we now have a self-animating face. All you have to do is type in the sentences you want to have spoken, and it comes out the other side, a virtual reality character that's animating perfectly. We have the ability to take a computer-generated image and re-synthesize it into a photorealistic image. That looks like a photorealistic city cloud, the image of a city. And yet what it started with was computer graphics, video game graphics. We have the ability to use this great technology called generative adversarial networks. Two networks. One trying to fool the other network by synthesizing a virtual human. The other network determining whether it's real or not. As a result of the two of them battling with each other, synthesizing more and more images of humans, while the other one rejects it, both of them become better and better and better at it, to the point where we're generating images of faces that don't exist. This is a virtual reality generated image based on artificial intelligence. We can even write music. We recently launched to celebrate the latest Star Wars movie. Disney and us partnered together to create a series of graphics cards based on the Star Wars themes. And to celebrate it, we decided to teach a neural network how to compose music like John Williams. This neural network has learned the music of conductors and composers of history. The Bachs, the Beethovens, and then now on top of it, we layered on top of it John Williams' style, and this is what they produced.
3, 4, 5.
Is that amazing? Composed by an artificial intelligence to mimic John Williams. Well, you've now seen artificial intelligence with the latest breakthrough from deep learning is able to achieve superhuman levels of computer vision. You already know that with all of the assistants that you use, from OK Google to Siri, it's now achieving superhuman levels of speech recognition. We can now generate virtual characters, synthesize and teach them how to speak and animate, and in fact, even generate music. We're now able to use software to write software by itself in ways that we can never imagine and achieve results that you're now starting to see. AI is going to revolutionize so many industries. One of the most important industries it's going to revolutionize is transportation. AV, autonomous vehicles, powered by deep learning and AI, is going to revolutionize driving, no doubt. There are 82 million accidents a year around the world. That results in fatalities, excess of 1 million, costs society $500 billion a year in damages. We spend almost an hour a day in commute. If we just assume that an average person makes $80,000 a year, 1 hour out of their 8-hour working day represents a fair amount of lost productivity. Not to mention, if you decide that you don't want to work, could you imagine having an hour of free time to be able to catch up so that when you finally get home, that you can spend quality time with your families? AV can save millions of lives and, frankly, trillions of dollars. AV is potentially the greatest revolution that will come to this industry in over 100 years. AV will also revolutionize mobility services. We already know there's plenty of traffic jams, but the amazing thing is, in another 10 plus years, a little bit more than 10 years from now, there'll be another billion people that come into society. 1 billion people. It's estimated that we're going to increase traffic by a factor of 3 times, from the 15 trillion miles traveled each year to over 40 trillion miles per year. Well, if every single car that we have, society builds 2 or 3 parking lots in anticipation of us, it's not possible for us to sustain 1 billion more people. And this is where the change and the technology revolution that's happening and social behavior changing with paying as you go is going to be incredibly important. We believe that AV can eventually drive the cost per mile of autonomous vehicles to essentially the same level, if not below, that of owned cars, self-driven cars. And so when that happens, it's possible, we believe, that AV could revolutionize mobility services. Not to mention just the imagination of what it could mean. You know, what would a car be like if it's not something you get into to get to your destination, but it is the destination. If I had a car that looks like that, I would love to spend an hour a day in it, but not do it. AV is going to revolutionize trucking. 3.5 million truckers each year transport 10.5 tons, $750 billion worth of goods across the United States. They're allowed to drive 11 hours a day with 10 hours off. 11 on, 10 off. Recently, with electronic logging devices mandated by law, the day that it was turned on, all of a sudden, the productivity of the trucking industry decreased by a factor of 10 to 12%. That basically says, because there aren't enough truckers, and because we're experiencing the e-commerce explosion, the Amazon effect, where you used to go and pick up your goods at the stores because you went to buy it, now you bought it on your phone and it automatically comes to your house. Somebody had to bring those goods to your house. Because of those changes in how we consume, the amount of truck drivers around the world is simply limiting. 10 to 12% loss in productivity. Could you imagine multiplying that by $750 billion per year? And so maybe here with autonomous vehicles and level 4 capability, for several hours on the road, we could make it possible for the truck drivers to take a rest and extending their range, keeping up with the enormous demand of the Amazon effect. Trucking could be revolutionized by autonomous vehicles. Now, at the core of all this is all the technology that we're all talking about. And in order to make autonomous vehicles possible, you have to solve this computing problem, this incredible computing problem, the largest scale computing problem of its kind, from the bottom all the way to the top. This is a processor architecture problem, an algorithm problem, a systems problem, a cloud computing problem, a car system problem, a sensor problem. The number of challenges necessary to solve in order for the automotive industry to bring AV to the world is just utterly daunting. Now, we've built PCs, laptops, game consoles, supercomputers, and I can tell you without exception, building a computer for autonomous vehicles is at a level of complexity the world has never known. This computer is on all the time, monitoring all of the sensors that's coming at it. It can never fail. It can never fail because lives are at stake. And it has to make the right decision running software the world has never known how to write. Incredible complexity. Well, with everything like that, because the opportunity is so great, because the contribution we can make to society is so enormous, we just have to tear it down one step at a time. And so the first step is we've got to build the fundamental processor. And so today we're announcing that the world's first autonomous machine processor, we call the Drive Xavier. The silicon is back, it is working incredibly well, and we're ready to sample it in Q1. It's the world's first autonomous machine processor. Now, whereas this chip here is the largest R&D effort and the largest chip the world has ever made, called Volta, 512 of those processors fit into another monster chip in my other pocket. I'm carrying in my back pockets, ladies and gentlemen, several $billion of R&D investment. One here, one here. Look at this chip, look how big it is. This is the largest SoC the world has ever made. Look at that thing. The largest SoC the world's ever made. In total, 8,000 engineering years to build this SoC. Let me tell you a little bit about it. So this SoC, yeah, we could turn that off real quick for a second. This SoC, the most complex SoC ever made, 9 billion transistors, 350 millimeters squared, made from 12 nanometer FinFET, 8,000 engineering years, as I've mentioned. But the important thing is this. Because of functional safety necessities, we wanted to make sure that we have the ability to have redundancy and diversity in almost everything that we do. Redundancy and diversity in almost everything that we do. One of the things that's really important about functional safety is that if a fault is discovered inside your car, it will continue to operate incredibly well. And so, how is it possible to build a computer that when a fault is detected, it continues to operate well? Well, the way to do that, of course, redundancy, diversity, an enormous amount of other technologies that I'll mention. Now, inside this chip, let me just very quickly mention it. There are 8 CPU cores based on 64-bit ARM, completely custom, 10 wide superscalar, 2700 spec in, basically approximately a server on a chip. All with ECC, all with parity. It also has this mode called dual execution. It runs everything twice. It runs everything twice without consuming twice the horsepower using this clever technique called dual execution. Volta GPU, our latest generation GPU, has the ability to process information in 32-bit floating point, 16-bit floating point, and 8-bit integer, so that the deep neural networks, depending on the type of detection you want to do, the type of deep learning network, it will all just run. One of the things that we know for certain is because every single deep learning network on the planet that we know of today is being developed on our architecture, we know that it will run on our architecture. There is no question whatsoever, every network that I know of will run on this architecture. There's 512 cores, which with this 20 tensor core tops, 20 teraops. I'll show you what that means in just a second. We also have a computer vision processor that has the ability to do stereo disparity, basically do the processing of the parallax between two cameras to calculate things like depth. Optical flow, how fast are features moving, in what direction are they moving, is called optical flow, and it does image processing. We have the ability to encode video for every single camera, 6 plus 2 plus inside the cabin, for every single camera in high dynamic range if something were to happen. Okay, so basically your black box, except every single camera is captured. We have the ability to process in full HDR from every single camera from our ISP, 1.5 gigapixels per second. Gigapixels per second. A camera has 24 megapixels. Think of that, 1.5 gigapixels. And then we have a brand new accelerator called a deep learning accelerator for the functionalities that we're very, very confident about, and we just want to have the lowest possible power or the highest possible energy efficiency. And we have 10 teraops of that, all supported by 256-bit LPDDR4. Let me show you what the computer looks like. Hey, Paul, which side are we on? Okay. All right. Well, this is a rigorous job. A lot of carrying. All right. So this is our Drive PX2. This is our Drive PX2, not this. This is our Drive PX2. This is the computer that all of the developers have been developing on. The Drive PX2 is 4 chips, 2 Parkers and 2 Pascal GPUs. 4 chips, okay? 4 chips, 24 teraops, 24 teraops. At the time that we delivered this to our developers, this was the fastest thing you could put in a form factor like this. This is 30 tops, this thing versus this thing. 300 watts, 30 watts. A lot of chips, 1 chip. Really heavy, barely feel it. And this is what you get for a few $1 billion of R&D. Well worth it. The world's first processor for autonomous machines. This, let me put that on this is the way you carry this, and this goes into your car. Okay, so this will power your future level 4 and level 3 autonomous vehicles. 1 single processor. You know what would be amazing? So the silicon came back 2 weeks ago. The silicon came back 2 weeks ago. And all of the developers, including ourselves, have been developing our software on top of this box. the beautiful thing about an architecturally compatible strategy, the architecture here is CUDA, the architecture here is CUDA, the architecture here is based completely on NVIDIA, the architecture here is based on NVIDIA. Well, this, we've been developing on for almost 2 years, maybe 3, and this came back 2 weeks ago. Would you like to see this running? Well, it's only been 2 weeks, so anything could happen. All right, so Mark, Gary, you guys want to show it to them? Anything could happen. All right, what's going on?
Scripted.
We don't rehearse, that's what happens. Okay, am I standing in front of something? Ladies and gentlemen, that right there is the Drive Xavier, the world's first autonomous machine processor, running the entire software stack, CUDA, TensorRT, the entire DriveWorks stack, and the entire Drive AV stack of perception and localization and ego motion and planning, all running there in just 2 weeks, guys. That's the power of architectural compatibility. So ladies and gentlemen, NVIDIA Drive Xavier, and we will be sampling it in Q1, and we should be in production before the end of the year. Okay, the processor is just the first step. On top, the reason why we know so much about what is necessary inside a processor is because we've been developing the entire software stack of a self-driving car all along. Hundreds of people have been working on this self-driving stack, from perception, ego motion, localization against all of the HD maps, using LiDAR, using computer vision, using radar, path planning, end-to-end stack. They've been working on it, and it's just an enormous amount of software. It's just an enormous amount of software, a whole bunch of technology that's never been developed before, a whole bunch of software the world's never written before. And over the holidays, Chen Yi Chen, one of our engineers, got into the car and drove 8 miles without touching the steering wheel. Homedale, New Jersey, December 19th. He went 8 miles, 23 intersections. 23 intersections. Look at this. No helmet. 23 intersections, 8 hard turns, 2 stop signs. You guys want to see this? All right, let's take a look. And so the computer, the processor, the system, all of the operating system, the system software, the never done before algorithms, all the way from perception to ego motion to localization to path planning, integration into the car. This is a giant step for autonomous vehicles. We're announcing today that Baidu and ZF, Baidu, as you know, is the internet giant of China, and ZF, one of the world's leading tier 1 OEMs, has selected the Nvidia Drive Xavier for their AV computing platform development in China. This is as you know, Baidu is making incredible efforts and incredible progress in China. Every single car made has to be China compatible. It is the largest market in the world. And yet, developing in China is very different than developing in the West. We created an open platform which makes it possible for us to develop the driving stack for the West and to partner with Baidu to develop the driving stack for China. As a result, every car that is manufactured with the Nvidia Drive Xavier and the Drive AV stack has an opportunity to be able to ship with excellent driving capability, autonomous driving capability for both sides of the ocean, in the West as well as in China. Super excited about the Baidu announcement. Baidu and ZF, thank you. Level 4 driving is incredibly hard. However, if there are places where the car goes that the car doesn't know how to drive by itself, you still have a passenger to drive the car. However, for a taxi service, for mobility as a service, obviously, without a driver in the car, that option is not there. And so every single possibility has to be considered. Well, the way to improve your odds and statistics for places you can go and different conditions you can experience and drive and navigate, the more computation capability you have, the more sensor backups you have, the more sensor redundancy you have, and the sensor types that you have, the better off you're going to be. And so whereas level 4 can be powered by one Nvidia drive, in order to do it for a robot taxi, we're going to need a lot more performance. And so what we've created for the level 5 market, all of our level 5 robot taxi partners, is the Pegasus, the Nvidia Drive Pegasus. It is powered by these two Xaviers that I've already mentioned, and look at these powerful GPUs that are on it. Okay, so this is a magical 400 watts, just 400 watts. And with two, either one or two, you should be able to power a robot taxi, a level 5 driverless car. Level 5 driverless car. Now the amazing thing is this we're going to be sampling this year, and hopefully sampling very shortly. This box right here, 1 year ago, this is now 1 petaflops. But 1 year ago, using our Pascal P100, it was 300 tops. 300 tera operations for deep learning. This is 320. It replaced an entire supercomputer in just one motherboard and 400 watts. The incredible progress and the breakthrough of our tensor core instruction and the Volta GPU. So this is the Nvidia Drive Pegasus. I'm super excited to announce that one of the most exciting companies in the startup industry, a company that was started by Chris Urmson and founders that worked on the Google self-driving car and the DARPA Challenge. They started a company called Aurora. They recently announced that they're partnering with VW and partnering with Hyundai to build their next generation autonomous vehicles. And they have selected NVIDIA's technology, and we're partnering together to build the autonomous vehicle computing platform. So let's come around. I'm also delighted to announce that Uber, the company that put mobility as a service on the map, has chosen NVIDIA technology, and we're partnering together to create future autonomous self-driving Uber. Ubers. Self-driving Ubers, guys. Sensors all over the place, LiDAR all over the place. These cars eventually will be able to drive without a driver at all, and hopefully reduce the cost of mobility below that of owning a car completely. Well, these platforms are not only powerful, as you can see, they're also open. We developed the entire stack of autonomous vehicle software so that we can offer it to people who would like not to build their own software, or we offer it to all of our partners in whole or in pieces so that they could take advantage of everything we have and differentiate in places where they would like, where they feel that they could do an even better job. And with the world being so large, $10 trillion industry, having a whole lot of people who are developing on the platform so that we can serve every nook and cranny of the transportation industry and enable autonomous vehicle capabilities is a fantastic thing. And so we created this open platform and we're working with partners all over the world. Last year, at this time, we had just a little over 200 software partners working with us, 200 development partners working with us. Today, we have over 300. Over 300 partners are now developing their car, truck, mobility service, computers as a supplier, their mapping systems, their sensor suites, maybe they're starting a company, or they're doing fundamental research. Whether it's Berkeley, MIT, Stanford, companies all over the world, developers all over the world are jumping on top of the Drive platform because it's open. And they could develop and create the future of autonomous systems. And so I want to thank all of the development partners for embracing the Drive platform. Thank you. Functionality is plenty challenging. The performance of these computers, the algorithms that have never been done before, the large-scale system integration with all of the different configurations of sensors is so complex. It is the most complex development we have ever done. And yet, that's just the tip of the iceberg. Ultimately, the most important feature of a self-driving car is not that it drives by itself. The most important feature is actually safety. How can you create a computer that in the event of a fault continues to operate safely for all the passengers involved? That technology, methodology, culture, tools, software, system design, that entire system, in order to enable functional safety, is extraordinarily complex. No system that has been functionally safe to the level of ASIL-D has ever been this complex before. People who are in the airline business and people who make airplanes are starting to notice the complexity of the work that we're doing and starting to knock on our door because they would like to take advantage of this incredible technology as we develop it. High-performance system, navigating through a very complex world, and yet completely functional safe. It requires a holistic system approach from culture to technology to tools. Our goal is to achieve ISO level 26262 ASIL-D capability, basically the highest level functionality of functional safety. I'm going to show you the system in just a second. And it includes everything from processor design. Every single core, every single IP on our chip has been touched by functional safety requirements. It's one of the reasons why it's so powerful that we design every single core ourselves. From our CPU core, full custom, our GPU core, of course, full custom, computer vision core, deep learning accelerator, our ISP, our video encoder, our video decoder, all of our image processing systems, the entire SoC. We have the ability to achieve traceability for as long as we shall live. If something were to happen, we can trace it all the way back to its source and continue to improve and mitigate for the future. There are 2 companies in the system software area where we partnered with. We've achieved levels of ASIL-D capability. BlackBerry with QNX, a real-time operating system that has already been certified to ISO 26262, and TT Tech, a time-triggered instead of event-driven operating system framework for applications to keep applications from stepping on top of each other. Okay, TT Tech and QNX, the 2 of them has worked with us to integrate their software on top of ours and with ours to achieve auto SAR. Now, building a computer that in the event of a fault could mitigate and control itself is one thing. But we want to make sure that the computer is designed properly, that is designed to perform properly for its intended function. Well, the way to do that, of course, is to test the car. But unfortunately, the number of miles, the diversity of experiences, the complexity of all the different worlds, the weather conditions, it is simply impossible to experience and put your car on the road to be able to test every single condition necessary. On the other hand, we would like to be able to control and have a repeatable environment so that every single time we develop software and improve software, we can test it against our entire regression suite. The only answer is really simulation. But how do you simulate a self-driving car without a virtual reality environment? Well, it turns out we know something about virtual reality. It turns out we know something about computer graphics. And so we've developed one of the most complex simulation environments we've ever done, which basically allows us to either, with software models of our entire driving stack that you just saw, or a hardware model of our entire software of our stack, and run it inside a virtual reality simulator. We call it AutoSim. What I'm about to show you is this. This is AutoSim, a virtual reality world simulator for your car. It runs on that computer, that supercomputer. The goal is we would run it at super real time. We would run this car in this world so fast that we can cover billions and billions and billions of miles over time. And we would like to be able to run it against 2 types of models. Either running it on the DGX, that again, with a software model, or run it on a Drive PX. Excuse me, Paul. This is where you go like this. Or you can run it on a Nvidia Drive.
Come on, Paul.
Nvidia Drive, for example, like the Nvidia Drive. Okay? Connected, running the entire software stack, connected to that machine, running a virtual world. Can you guys see that? Okay? So this is hardware in the loop. And so why don't we take a look at that? Mark.
Hi, Jensen.
Hey, Mark. This is Mark David, guys. All right, so why don't you take it away?
Okay.
Yeah, take it away.
Yeah, well, so this is a little configuration of our virtual environment. We want to show you that we can change some of the parameters of our world and some of the parameters of our car. So let's play with the world a little bit first. I'm just gonna do a few fun little changes and move the sun. Let's bring it down, make it a little closer to a sunset. Get a nice little glare off the road. And one of the things I love to do, we can't do on planet Earth, but we can do in our simulator. Let's move the sun this way. We can cast shadows across the road. That plays a lot of havoc with sensors sometimes, or cast them the other way. Or put a nice big glare in the driver's eyes. A nice specular highlight coming off the road.
And as you know, one of the things that LiDARs and cameras are most scared of is direct sunlight. Okay? All right, next.
Okay, so that's our environment. Let's jump over and configure our car. Now we're looking at, if you look on the right side of the screen, we got 4 cameras hooked up to our car, and we're looking at the front camera right now. Let me run over and play around with that front camera a little bit. So first of all, I could simply move it anywhere I want to in the environment. Over to the driver's side, over the passenger side. Maybe I want it toward the front of the grille of the car.
And maybe you're using exactly the same chassis and the same computing platform, but the design, the industrial design of the car is a little different, and so the placement of the camera is a little different. And before you go and build that car, you would like to be able to configure the cameras accordingly and run quick simulations to make sure that against the billions of miles that you already collected up, it's going to work.
That's right. And let's move over here and let's configure one of the other sensors. Here's my right-hand camera. One second. Right now it's focused almost directly to the side of the car, but I might want to look a little further toward that blind spot toward the rear of the car. I can simply rotate that camera and boom, I'm looking at the rear of the car.
Okay, that's cool. Let's run it.
Okay. Now that's our environment. Let's run the simulator.
Okay, remember this is the simulator and that is the Nvidia drive. Now remember this, because the architecture of Nvidia drive and the architecture of that supercomputer is identical. It's binary exactly the same. So we could take the entire software stack that runs on this and run it inside that software in the loop. Does that make sense? Okay? This is one of the great things that we can do as a result of using an architecturally thoughtful approach to developing the self-driving car. All right, go. All right, on this side is the simulator. On that side is the car driving by itself inside the simulator. The entire stack is exactly the same. It detects lanes, detects cars. Detects lanes, cars, signs. Basically exactly the same software stack. Okay, Mark?
And once again, one of the beauties of the simulated world is we can set up some kind of dangerous situations you do not want to do on the real road. We got our friend merging here. No!
Whoa! Okay, that was close.
We can see that our auto drive hit the brakes as this guy made a not too kind move. And
okay, so
that's
that's
in a simulated world.
So that's software in the loop. Can you guys do hardware in the loop?
Of course we can.
Exactly the same software tool, exactly the same software stack. We're now simply going to replace the software module and slide in this hardware module. Okay?
So let's switch over to see it. Okay, so now we're actually running on a Drive PX2 as the hardware in the loop, and the simulator is showing this virtual world.
Now,
oh my reason! We found a new driver, so we're actually interactively inside of the simulator driving another car, manually driving another car.
Okay, now you can see that this is RGB. The reason why, hey Curtis. The reason why you see it on this screen in orange is because the color space is different. And that's the beautiful thing. The fact that you saw it differently says that's exactly the way that Drive was seeing it, and the whole Drive AV stack was seeing it. We changed the color spectrum so that we can extend our low light capability. Okay, so there's some colors that just simply look different, but as a result we have a much better high dynamic range. And so Curtis is basically driving the car in the simulator, and Drive is responding to it. Over here, you see, every time Curtis gets in front, our automated driving system applies the brakes. Meanwhile, we continue to stay in the lane and mind our own business and continue to drive while Curtis enjoys himself. And so what you're seeing here is something that we could, of course, pre-record, and we can capture these different scenarios and put it away. And whenever we have new software stacks, we run it against this entire scenario in super real time, and bam, we know that whatever improvements we've made has no regressions. Okay, one of the most important things we're working on is functional safety. Functional safety includes processor designs, all the redundancy, the resilience capability associated with it, from ECC to redundancy backbones, and clock checks, and voltage checks, and all built-in self-test. And the chip is basically a tester and tests by itself. Every one of our software stacks is going to be ISO 2626 certified. And one of the things that has never been done before is to use it to ISO certify a deep learning compiler and a deep learning runtime. A neural net has never been ISO 2626 certified before, and we're going down that process to make sure that it's completely ISO 2626 certified. As a result, we have a computer that could detect faults, whether it's soft or hard, and mitigate. However, in order for us to be truly functional safe, we have to have a robust testing and validation strategy, and that's why the simulator comes involved. And the type of simulators you want to create for designing something like a mechanical system is what you're seeing here, a virtual reality simulator that has software in the loop as well as hardware in the loop. In our case, completely binary compatible so that we don't have to change the code before we test it. If you have to change the code before you test it and something were to happen, where did you insert the fault? Was it in the code or from the things that you tested and you changed? And so the ability to be able to software, run it in a software binary way and to know that the results can be exactly the same way is one of the fundamental advantages of our approach. Okay, so functional safety. Thank you very much, Mark. This computer does three basic things. Sensor input. From that sensor input and sensor fusion, it's able to perceive the environment, reason about what to do, and take action. Path plan. Okay? So perceive, action, take action, a reason, and then take action. Another way of saying in self-driving car speak, perception, localization, and path planning. Well, it turns out that those three steps are the fundamental steps of almost any autonomous machine. And one of the things that we would like to do is we'd like to turn the whole car into an autonomous machine. The whole car. Your car in the future should essentially become an AI. And the reason for that is because it has sensors all around it, has cameras all around it, ultrasonics all around it, it's got LiDAR all around it, it's got cameras all around the inside of it. And you need the AI to be in the car because it's not possible for the cloud to understand the context around you. The cloud is not going to see all the cameras. The cloud is not going to see all the passengers in the car. The cloud is not going to be able to see where's my eyes looking, where's my head pointed, what's the traffic around the car, who's walking up to the car, what face is looking at the car. And so those kind of contextual awareness capability has to be resident in the car, and as a result, we have to turn the car into an AI. Now, in the future, every car is going to be self-driving. There will be millions, 100 million cars built each year. Because of the number of miles that we have to deliver for mobility as a service, there will be millions of robot taxis built, and several 100,000 trucks built each year. Every single one of them will have autonomous capability, both to either drive by itself without a driver, or to augment the capability of the driver. Well, that baseline capability is the future of AV, but on top of it, we believe what's going to really define your driving experience is the AI that the car companies create for the car. Your driving experience is going to be defined by the industrial design, the wonderful interiors that they create, and the AIs that is written. And so what we've done is we created an SDK. We created a platform that allows artificial intelligence capabilities to be exposed to application developers. It has surround perception, speech recognition, speech synthesis. In the future, you should have a conversation really just basically at human rates, be able to cut each other off, and the car will still be able to understand exactly what you're talking about. It'll have natural language understanding, understand what you meant, open the window, it understands which window to open. Turn it up, it'll understand that you probably meant the radio. Eye tracking, know where you're looking, and compare it to what's happening outside to make sure that you're looking in harm's way. Head pose, making sure that between the head pose and where your eyes are looking, that you're looking in the direction of the points of interest. Gesture recognition. You may decide just, oh, hold it down, you know, just like that, and it'll know exactly what you meant. All of that technology all of that capability powered by deep learning and AI are going to be exposed because this capability is already in the system. This computer is able to perform the deep learning capability necessary for all of these incredible AI abilities. And so this is part of our system called Drive IX. Again, exactly the same computer, exactly the same computer. You could run it on the same computer, or you could run it on another processor, another Drive Xavier, and the second Drive Xavier could be the backup for the first driving computer. And that runs the Drive IX. Well, if I have all of this capability, all of the surround capability and sensors, and we have computer vision capability, and I know where I am, I've localized myself, I can track everything around me, and I've got amazing computer graphics, you would think that I could take the way that we engage cars to the next level in the future. We know that the way we engage computers in the future will be based on voice, based on gesture, based on facial recognition, and of course, it will communicate to us based on augmented reality. And so today we're announcing a brand new platform called the Nvidia Drive AR. It's a software stack that runs on exactly the same computer. We know that augmented reality is going to define the future of user interfaces. It's going to be, if you had a car that you ship in 5 years' time, you will simply not understand if it can't have a conversation with you. In 5 years' time, you will simply not understand if it doesn't have augmented reality capability. You should be able to look right out either a head-mount display or the infotainment system, and graphics that highlights the things that it sees and the points of interest are perfectly registered to it. It almost looks like the computer graphics is right there in the environment. Well, we're putting the whole system together. You're going to have to take my word for it that the next time I show it to you, it's going to be a lot better. That was a joke. It's pretty good now. And so why don't we show it to you? Hey, Justin, you were supposed to get ready.
All right. Well, I'll get ready now. While you get the
all right, you get ready, you get ready. Okay, so this is what we're going to do. We're going to show you something that's really cool. We're going to show you something that's really cool. Justin is going to get into a virtual reality environment. He's going to get into a virtual reality environment. The environment is called holodeck. Okay? And this holodeck, wait, don't go in yet. Don't go in. Now you're getting ready. Okay, this holodeck is really amazing. It's going to have a car inside. And this car basically runs this entire stack. Okay? It's going to have surround perception. It's going to be able to detect the objects in front of it, and it's going to recognize, localize itself, track all the objects, and register computer graphics on top of it using augmented reality. All right, go in there.
All right. Yeah, so it turns out that explaining and...
Just remember, you're the only person in VR. The rest of us are watching you.
I know, I'm going to go
okay,
really
remember, slowly now, slowly.
So, creating concepts for user experience in automotive is really difficult. And so we created this virtual lab to explore it. Around each on my side, you can see the 6 input cameras that are the sensors that come in to allow the car to drive. Okay, if I go over closer to the vehicle and look down inside, you can see a concept for an augmented reality cluster and rearview mirror, digital rearview mirror. So I'll climb inside.
Can you guys see this? All right, so that digital dashboard is running the Drive network, and it recognizes the path that it has to drive, the objects around it, and if you look behind you, nice and slowly, look at that. So he's inside this augmented reality environment, and we're basically taking the simulator we just talked about. Do you guys know what I'm talking about? We're taking the simulator, we took the videos that we captured while we're driving our test car, and we can now test that video against a virtual reality car running inside a holodeck, running our entire software stack. Pretty amazing, huh? Okay, so we imagine that in the future, when you look down into your infotainment system, it will detect all of the things that are important so that you have direct feedback from the artificial intelligence self-driving car, what it sees in the environment around it. So that you have confidence that it recognizes the important things and you have confidence that it's going to drive carefully. It's also going to be able to augment on top of it points of interest. And so you could say very naturally, where's the local McDonald's? And it will literally navigate your way there, render the computer graphics path that it's about to take, and then when it gets close, McDonald's shows up. Okay? And some computer graphics will be sitting on top of it. So all of the fundamental technology is now made possible by this SDK. The rest of it is application development. All right, Justin, thank you very much. Good job. Okay, I want to share one more thing with you guys. It's something that's really, really exciting. As you know, this car that we demonstrated it in is not likely the most likely car to bring artificial intelligence to the whole world. Okay, this is the best way to bring artificial intelligence to 100 people in the world. And what we want to do is we would like to revolutionize how people drive, how people move from place to place, how goods are moved, but also revolutionize the way that we interact with our car. And I can't imagine a more important company, and I can't imagine a more proper company to take this technology and change everything that we all know about cars. And so today we're announcing that we're partnering with the largest car company in the world, Volkswagen, to revolutionize the future of cars and to infuse AI into the future line of cars so that we could bring joy and delight and just incredible surprise to people who enjoy cars in the future. And to help us talk about this and the impact of this, I'd like to welcome Dr. Herbert Diess to stage, the CEO of Volkswagen. Herbert, great to see you. Great to see you. Good to be here. Guys, Herbert, you know this, but you know, when I discovered deep learning, when I discovered deep learning, I was so excited. I was so excited. I had to go show it to somebody. You know, this is one of those things where you, oh, I found it. You got to show it to somebody. And so I packaged it all up. I flew it to Germany, and I went to show it to Herbert, to Dr. Diess. And I said, this thing is amazing, Herbert. You give it anything you want, and it will recognize it. He says, come on. I said, no, I'm serious. We didn't write any of the software. The software learned how to write itself. We simply trained it with a whole bunch of data, and now it can recognize anything. He goes, oh, come on. And I said, no, try it. Just, you know, throw something at me. And he goes, well, look, we have this dog in Germany. Everybody has it. And so I'm gonna give you this dog. And if you know, look, it's the most popular dog in Germany. And I'm going, oh, I tested German Shepherds. I'm so good. This is so covered. And he goes, Dachshunds. And we looked up the dachshund, we pulled in the image, and our deep neural network had no clue what it was. And that was the end of that meeting. I pretty much packed it up and I said, we waved goodbye. So years later, it does work. It does work.
Yeah.
And so Dr. Diess, well, you know, I just enjoy calling you Dr. Diess.
Why that?
It sounds good. Okay. But Herbert, you're the CEO of one of the most storied, one of the largest car companies in the world. And now we're seeing a time when technology transformation is happening to the car industry like nothing that we could have possibly seen, all at the same time. And so when you're in the middle of this incredible opportunity, what does it look like to you? What do you see?
First of all, I'm very excited to be here and very excited to experience that show because it shows the dedication. And also I wanted to congratulate you on your progress. Now it's really working now. It's working a lot better. And the meeting was not finalized when
it was funnier the way I told it.
We continued. But I'm really excited to be here, and I also wanted to congratulate you to your achievements, which are stunning. And I'm also excited because a lot of your power, motivation, resources go into automotive. And I think you get that feeling, everyone has that feeling that the automotive world will change a lot the next 10, 15 years. You showed many things. I think it will be more exciting than today. Cars will become even more important, more exciting, sexier than today. The industry will change a lot. I think driving will be totally different to today. The car today is already, we love cars, or most of us love cars. We love the brands, we love designs, we love the performance of the car. If you drive in a Volkswagen, it's fun to drive, mostly. So it's an exciting.
It's perfect,
but it has negatives.
Right? That's perfect.
Yeah, sure, but it has negatives, and you mentioned those. It's accidents, and it's also pollution.
Yeah.
CO2, other exhausts. And this will change a lot. So the car will lose a lot of its negatives and gain much more positive things. It will be much more comfortable, it will be safer, and it will be environmentally friendly. So putting all those positives to the car, I think the future of the car is really very exciting, brilliant. And many people also think that it will be a lot of shared mobility. No? We all will drive in boxes around which go autonomous taxis. I'm not so sure about this because a car is much more than transportation. A car is fun to drive. You want to express yourself with a car. You want to drive the right brand, the right design. I think we will spend more time in the car because traffic jams won't go away. The demand for mobility will increase. So if you spend more time in a car, if you can do work or games or whatsoever in the car, then I think you still would be interested not in only a very neutral shared car, but you want your own environment, your own smell, your own taste, your own music. And that is why I think that individual cars, properly designed, exciting cars, emotional cars like this will have a bright future. And what I've seen today is, I think, is very encouraging. We will see a major change in the next, as you said, 5 to 10, 15 years maximum, 2 life cycles. And
it's amazing, isn't it?
It's amazing, yeah.
Yeah, just 2 life cycles. And here we are, the way that you designed cars in the past, of course, the mechanical elements of the car, the engine design, the electronics are all incredibly complicated. And these are heavy things, and they last a long time, and they have to be safe. And all of a sudden, you're pushing your company to electrification. And now the internal combustion engine is not necessary. You're driving your company to artificial intelligence. And now the software component and the computing component of the car and its architecture is now so important. You're going to have your cars, because I remember hearing you talking about the 3 passionate directions that you felt, that it had to be electrified, it had to be artificial intelligence, and it has to be connected, so that you can continue to upgrade the car for as long as you shall live, and make the car user enjoy the car and delight the customer for a long time. So these 3 elements fundamentally changes everything that you do.
Absolutely, absolutely.
Right? I mean, the nearly 100 years that Volkswagen has been building cars are now looking forward completely different. How do you think about that?
I think still we need some of those skills. No, they are still necessary. We are producing cars worldwide. We have to ramp up plants. We should produce many cars, and it's not so easy to copy that. No, as one can see. So we have capabilities which we still require. Cars have to be safe. Also, they need a passive safety for many years. No. But we need new skills, and I'm very happy that your company and yourselves is really dedicated so much resources, because what we need is AI. What we need is sensors, a lot of silicium, a lot of software goes into the car, and we need a new understanding of how to work together. And that is why I'm very happy that we know each other since many years, because the interaction between, you have been a second tier for many years now, but the interaction between the software and hardware developers and the OEMs must be much closer. I think we are getting this way to be really fast and makes it change together.
Yeah, and for the audience that doesn't understand the automotive industry speak, the OEMs, the first tier is the manufacturers that directly contributes and manufactures things for them. The second tier is the technology provider that builds for the suppliers, the tier 1 suppliers that delivers the systems. In the future, because technology is so complicated, it is but yet the tier 1s are still remain very, very important, that we will work in a triangle model. And so we all have to collaborate a lot more closely further up front and for a lot longer after development. And so that's what Herbert is describing. Now you know, the thing that we've learned is just so much, and you're absolutely right that on the one hand, we know very much about building computers, and we know very much about developing software, and we know a great deal now about artificial intelligence. But how to adapt all of that technology into a car that can ship in hundreds of millions and drive for years and years and years and keep people safe, that safety sensibility, that safety culture, we've learned just a tremendous amount working with your company. And so that's something that's been of great value to us.
Yeah, I think it's also for you a challenge, to work on the ASIL levels, to do hardware in the loop, which is probably not.
Until I met you, I didn't know what ASIL stood for.
I can imagine. No?
Yeah.
So it's for you as well a challenge, but also for us and for the whole industry.
Herbert said, "Hey, what do you think about ASIL?" I said, "I don't want it." No thanks. I'm good. No, I'm good. Would you like some ASIL? No, I'm good. I'm good.
But you have to.
Yes. Now I'm ASIL D. I'm just not ASIL B, A, B, C. I'm ASIL D. I've got the religion and some.
And I'm very happy that you're
Yeah, no, man. I'm going to be the flag bearer for ASIL D functional safety.
No, what I wanted to say is that it requires also different architectures from our side. Now, so far we have been relying on many computers in the car, 60, 70 small microcomputers doing the task for controlling the engine, the brakes, the ABS systems. That will be different. We will have only 3, 4 major computers integrating the separate software from hardware. So far we bought most of those chips with the components, so the engine came with the engine controller, the ABS came with a brake controller. That will change. So we will do the hardware, and I'm very happy that you're also investing in hardware stacks and in software stacks and also in SDKs, which we definitely need, because the car will be much more complex today than today. We will have part of the software running in the back end. That makes really, that's a big challenge for all of us. We cope with that designing an entirely new platform, which is fully electric. It comes with 5 new models starting in 2020, 2021. We hopefully will deliver the bus with a totally new user interface, totally new touch and feel in the car, but also with a totally new software and hardware architecture. You only can do this if you really start from scratch. So we left everything behind. It's a totally new platform, not only the hardware, but also the computers, the software, and later also components for autonomous driving and the artificial intelligence in the interactions.
You know, and it's really amazing to see the transformation that you've made in the last several years. You know, today, our engagement with VW, there are lots and lots of people who are developing AI software. We create the SDK. However, you're going to turn that SDK into the experiences that touch the users and surprise them and delight them. And people don't realize that in the future, a car has a very large cloud component. And so there are data centers that you're building and working very closely with your IT department and building out data centers. And so the cars of the future are just magnificent in their complexity. And it's the greatest challenge in technology ever. But in the final analysis for the customer, it is still the emotion of the bus. And so I got to tell you one more story. So I came to Las Vegas for the very first time 40 years ago. And I was just an early teenager, and I played a lot of table tennis, and it turned out that the US Open was right here at Caesar's Palace. And so my coach packed a few of us down into a car, which was Volkswagen micro bus. And we drove all the way down from Portland to Las Vegas for the very, very first time. It was my first time in Las Vegas, and to play at the table tennis tournament here. And it was blue. I loved it because it is not only a car, but it's also a hotel. It is. It's also a hotel. I lived in that car for almost a week. And so I have a surprise for you. Okay. We decided that we would like to bring this to life and let people enjoy it. Several years. Now, you know, Herbert, you built this car because the demand for society, people are asking you to bring this car back. And so you decided to build a bus. And we decided to bring it to life years before that it will actually be enjoyed in person. And so, ladies and gentlemen, please, we have the buzz for you in virtual reality. And so you stand over there. Hey guys.
Hey Jensen, how's it going?
Hey Sean, let's show Dr. D's, let's show Herbert his baby here. This is the future Volkswagen. Go ahead.
Let's bring it up.
Oh, it's exactly the same one.
The right one, right?
It looks exactly the same after all these years. I love it. It's fantastic. Boy, this brings back memories. Except I think the one I traveled in actually had a bed in the back. I think I've been in ones with bed in the back, kitchens in the back. Some of them had chairs in the back. All right. So, but let's modernize it, shall we?
Yeah, I think we have a newer one that we can look at too.
And so everything, Herbert, everything is virtual reality. We're going to put this in our booth so that everybody can come and see it. We're going to make this available for your team so that you guys can put it in the cloud, and we can stream it to millions and millions of people for them to enjoy, and let them start to see the amazing design that you guys came up with. Wow. Okay, show us around quickly.
Yeah, let's open it up and take a peek.
Look at that.
That's when you're a feature. No, sitting face to face makes a huge difference in a car. Yeah?
Well, the buzz is the perfect place to do that.
Exactly.
Now, when eventually, of course, when the bus is driving by itself, this is a good way
Absolutely.
to enjoy it.
And the design will be such that there is a space between the front seats that you can get back in an autonomous driving situation.
That's amazing.
Yeah.
Wow, look at that. It's just like one big moving living room. Beautiful sunroofs. Okay, what else?
Okay.
These guys could travel at warp speed.
Well, I think we need some tunes, right? Where's the radio in this thing? a little more messy.
But you know, whenever you're with a Volkswagen bus, you're partying.
Okay.
So this isn't just about getting there. This is yeah. There you go. Okay. Ladies and gentlemen, Dr. Herbert Diess is such a great honor to partner with you. All right, thank you. Thank you. Congratulations. Thank you. This is going to be incredible. So we're going to partner with Dr. Diess. We have teams assembled, and we're going to infuse AI throughout this entire platform. From the way you engage, the way you navigate, to the way you drive, AI will define the future of all of your cars. As I've mentioned, the complexity of autonomous driving, the complexity of the software of future cars is incredible. It starts with, of course, building a brand new type of processor we call the Drive Xavier, an autonomous machine processor that is able to do deep learning, perception, has the ability to do parallel computing, and also computer vision, and high-performance computing at very, very energy-efficient levels. It's got a rich software development platform because the amount of software that we have to develop for this thing is enormous. This is not an embedded controller. This is not a detector. This is a computer. And it's a computer that's going to have tons of software that's never been written before, and so we need a rich software development platform. It has to be functional safe. ASIL-D, ISO 2626, this level of capability requires a complete redesign and rethinking of everything from the way you architect your processors, the way you develop your algorithms, the redundancy necessary, the resilience necessary, the diversity necessary. All of that has to be completely rethought. And it includes a simulation mentality. And we've created an open platform so partners all over the world can take advantage of the technology that we've created, but also put on top of it their own. Because the transportation industry is so absolutely enormous, $10 trillion. It's impossible for any one company to do it all, but it's possible for us to work together on an open platform to be able to engage it. And so you take a look at our entire stack today. Drive Xavier is the computer, Drive AV is the autonomous driving stack, Drive AR is the augmented reality navigation system, and Drive IX, intelligent experience that turns your car into an AI. Thank you very much for coming to our CES keynote. It's a great way to start the year. This year, we're going to see some amazing technology created. Today, we announced our Xavier will be sampled very, very shortly. It'll be sampled in Q1. It's performing incredibly well. It's the world's first autonomous processor. And we talked about the 3 platforms that I just mentioned. We talked about the Nvidia Drive Functional Safety System. And we announced 4 incredibly exciting partners and anchored by one of the largest car companies in the world, a car company that can take AI and make it part of our lives for hundreds of millions of people all over the world, Volkswagen. Thank you, Dr. Diess, for joining us today. Thank you, everybody, for joining us. Happy New Year, and have a great CES.